All right. So we're going to see what you had in this chapter, and then we do some example problems. This is showing a magnetic force on a moving charge with charge Q with velocity V, and it is in the magnetic field B. So as you see, this is the charge moving at this velocity, and the velocity vector makes an angle phi with the magnetic field that's present. And the force is given by this formula, and you see it follows the right-hand rule, because B cross B it requires a right-hand rule. It's perpendicular to both V and B. And if the angle between V and B is 90 degrees, you get maximum force. And in general, F is QVB sine phi. But when sine phi is 1, you get maximum force. And then we applied that idea to a charged particle moving in a magnetic field, like in this, goes around a circle, and the force QVB in this case, because they are in perpendicular direction to each other, V and B, is equal to mv squared over r. V cancels, and you can solve for r. So it goes on a circle of radius r that's given by mv, momentum of the particle, divided by qb. And v, of course, is 2 pi r over t. T is the period. 2 pi r is the circumference. And therefore, t can be written as 2 pi m over qb. And if the particle is not going perpendicular to the magnetic field, it has a perpendicular component to the magnetic field and a parallel component. And as it is going around circle with the perpendicular component, it goes along the magnetic field with the parallel component of the velocity, and therefore it goes on a helical path, which has this radius, which instead of V, you have now V perpendicular. And we did some examples regarding that. And then we talked about velocity selector, which is application of this magnetic force. We said that if you have a magnetic field that's into the page like this here, and electric field perpendicular to that, and the particles are moving perpendicular to both of these magnetic and electric fields, then the particles that have exactly this velocity E over B go right through without deflection. All the other particles deflect. And when we have a wire of length L and carrying current I in a magnetic field, we have a magnetic force acting on it, because this current is made up of moving charge particles. Therefore, we can calculate the force on a wire of length L in magnetic field B and carrying current I by this formula. Instead of QV, we have IL cross B. And if you have a more complicated situation where the wire is not just a straight wire, and it is not in a uniform magnetic field, you can calculate the element of force acting on an element of current as I dl cross B be present at that element of current on the wire. So then if you want to use this, you need to add all the contributions, which means integration over the length of the wire. All right. And then we said that if you have a loop of wire, particularly if you have n rounds in the loop, we define the magnetic moment of the loop, or magnetic dipole moment of the loop, as NIA, where n is the number of loops, number of turns in the loop, and I is the current in each one, and A is the area of the loop. And then we see that there's no force acting on the loop in a uniform magnetic field, but there will be a torque acting on the loop. And the torque will be mu cross B. Mu is the magnetic dipole moment vector, which is perpendicular to the plane of the loop and given by right-hand rule, as you see here. And of course, we have energy, potential energy due to the magnetic dipole in the magnetic field. Okay, now we have this problem. It says the figure shows a circular coil of radius r, 15 centimeter. Here it says 5 centimeter, but I think I changed it to 15 centimeter. With 130 turns of wire, lies in a horizontal plane, which we call XZ plane. It carries a counterclockwise as viewed from above. See, if you look from here, you see that the current goes like this, counterclockwise. Of course, if you look from below that, you see that the current is going clockwise. That's why it is said, it is asserted that it should be looked from above. Current is 5 amps, and it is in a uniform horizontal magnetic field B equal to 1.2 Tesla, directed to the right that we call X. So by saying all of these, it actually defines a three-dimensional coordinate system, that X is to the right, Z is in the same plane as the loop, so it will be this way, and Y is up. Now it says find the magnitude and direction of the net magnetic force on the coil. So I want to ask you, what is the direction of the net magnetic force on the coil? And I want you to answer with the poll. This should be quick if you paid attention. All right. All right, I'm going to end the polls. All right. Anyone wants to say why they chose what they did? All right, we have an isolated answer F. Who said F?
I did, but it was a stupid choice I did.
No, that's the correct answer. So I wanted to see.
Oh my God, so I was right.
Yes.
Okay, so I thought it was a stupid choice. Okay.
No.
Because it sounded surreal in my head. Okay, well, I guess I was right. I don't know.
All right. So you see that only one of you said by chance, apparently, correct answer. Do you remember we said that the magnetic force on a loop of current is 0 always. The torque is non-zero, right? Remember we said if you look at this, the force on this one, on this part, is I cross B. Let's say B is in this direction, I cross B is up. For this one is down. For this one, whatever it is, for the other one is opposite. So the 4 forces, they actually cancel each other. But the torque may not be 0. The net torque is not be 0, but the torque is given by tau, which is mu cross B. So the answer is F. Next time, pay more attention. All right. Now it says, which side of the coil tends to be lifted by the magnetic field? And again, I want to give you the poles. What do you think? So the torque is non-zero. Torque is mu cross B. And now we want to see which side of the coil is tends to be lifted. And let me remind you of the formula I just showed you. Mu cross B is the torque. So here, and while you're thinking about it, I'm going to show this. This is the X direction, and this is Y direction, and Z will be this way. So that the loop is in the XZ plane. All right, any more takers? Which side of? Anybody else? This is, you see you have B in this direction, and you have mu in this direction. All right, I guess that's everyone. I'm going to end the poll. All right. Now we have 100% improvement. This time, 2 of you answered correctly. Who wants to talk about it? All right. All right, you see, tau, it is, I think, the problem of understanding the torque from mechanics. And now we said that the torque acting on this is mu cross B. Mu is up, B is to the right, and from right-hand rule, mu cross B, do you see if you put your 4 fingers in the direction of mu and then turn into B, your thumb shows into the page, means in the negative Z direction, right? Everybody sees that? Z is out of the page, I mean, toward us, and mu will be into the page. So, sorry, tau will be into the page. So tau is this way, right? Which is into the page in the negative Z direction. And then now we want to see how does it turn. Of course, this turns the loop like this. Means that this side is going to be lifted, this side pushed down. So the left side is the answer. Okay. Is it clear? So you see that the torque is, if I want to show, the torque is into the page. That means that if you put your thumb in that direction, your 4 fingers show which direction this is going to be rotated. So therefore, the left side is pushed up, the right side pushed down. All right?
So the left side's pushed up because of the clockwise motion, you mean?
No, because you see, if the current is this way, is going out, right? The current is going out, and the magnetic field is this way. So I and B, right? Now you can think about the force acting on that part of the loop. You can think of it that way too. So we said that force of is IL cross B, I or DF, let's say, I DL cross B. DL is in the direction of the current, right? So if you put your fingers in the direction of I turn into B, your thumb shows the force.
Yeah, I see it now. Yeah.
All right.
Yeah, I got it. Thank
All
you.
right, very good. All right, that's, these practices are for learning. So you're learning now. That is the whole purpose, right? So you can think about tau being into the page or in the negative Z direction, and then you put 4 fingers in the direction, sorry, you put your thumb in the direction of the tau. Your 4 fingers shows which direction this torque tends to rotate the loop, which is, as I said, it is this way. So it means that this side goes up. Or you can say, okay, at this point, there is a current going in this direction. The field is in this direction. Again, I cross B, L cross B, L is in the direction of I. L cross B is again up. In this point, you see the current is going into the page, and field is this way. And you put your fingers in the direction of the current, turn into B, your force is down. So there are a variety of ways you can see that. Okay? And here, the current is in the direction of the B field, so there's no force acting on it. In here as well. Okay? So for you guys to be fluent in this, you need to consider different situations and practice these. And by that means basically going through the problems and thinking about the solution. And this is practice that you need. All right, so this side is going to be lifted. This side is going to be pushed down. All right. Any questions? All right. It says find the magnetic dipole moment of the coil in unit vector notation. Means that we want magnitude and direction. Magnetic dipole moment. We said that it actually is showing here. Magnetic dipole moment is vertically up. And as I said, this is X. The B field is in the X direction. This is X. And Y is up. And Z is in this plane this way. So if you have that, then you see that mu is in what direction? In the Y direction, isn't it? So we know that the direction is Y, so or J hat, and then if magnitude mu is NIA. Number of turns times current in each turn times the area. So therefore mu is 130 turns. See, it says 130 turns. I is 5 amps. And then area is pi r squared. So this will be 650, right? No. Yeah, 650. 650 times pi times 0.15 squared. So whatever that is. So if you calculate that, will be 0.15 squared times pi will be 0.0707 times 650 will be 45.9 or 46 almost. 46. What is the unit of that? Amp meter square, right? Because N doesn't have a unit. I has units of amps and area is meter square. All right. So this is mu. And if you want to write in unit vector notation, so mu vector is 46 J hat in amps meter square. So this is mu in vector form. Any questions? All right, now it says, find the magnetic torque on the coil in unit vector notation. So again, we found mu to be 46 J hat in SI units. And then B, because torque is mu cross B. How can I write B in unit vector notation? B as a vector becomes magnitude of B times the direction, I hat, right? It's in X direction. And therefore becomes 1.2 Tesla times I hat. So here we have mu is in J hat direction, B is in I hat direction, and torque becomes mu cross B. And therefore can multiply the magnitudes. So if you multiply the magnitudes, 1.2 times becomes 55. 55. The units will be Tesla amp meter squared, will be Newton meter, 55 Newton meter. What is the direction? J cross I. What is J cross I? Negative K hat, right? So it comes negative 55 K hat Newton meter. As I said, the torque will be in that direction because mu B, right? Mu cross B will be in that direction, and that is negative Z direction. X, Y, Z. All right. Make sense? Any questions? So you see, it is very simple, but you just need to set it up and look a little bit carefully at what's going on. All right. Here's another example. The rectangular loop of wire has a mass of 0.15 gram per centimeter of length and is pivoted about side AB, as you see here, this side, on a frictionless axis. The current in the wire is 8.2 amps in the direction shown. The direction is this way. This is actually shown here, but it could be when it moves, it will be like that. Find the magnitude and direction of the magnetic field parallel to the y-axis that will cause the loop to swing up until its plane makes an angle of 30 degrees with the YZ plane. So that as it's shown here, angle of 30 degrees. So if you look at that in this direction, you see this figure, right? You see, this is the loop in red, and then the gravity wants to turn it back to where it was, but there is a magnetic torque pushing it this way, and therefore it makes an angle of 30 degrees here, right? Is that understandable?
Professor, you cut out for a tad bit. Can you repeat all that?
Sure. So if you look at it this way, oops. Look at the situation along this direction, along Z direction. This is what you see. You see XY plane, and the loop is like that, right? And the weight of the loop, mg, which is acting from the center of it, is tending to rotate it back to the vertical direction. But the torque of the magnetic field will turn it up so that it stays at this 30-degree angle. Does it make sense?
Yeah.
All right, so the question is, this torque is from a magnetic field, which says in the direction of y-axis, field parallel to the y-axis, but we want to know whether this field should be up or should be down along the y direction. Should be this way or should be this way to cause this rotation. What do you think? If we want the torque to be in this direction, I mean the rotation to be in this direction, what is the direction of the torque? I just said you can use right-hand rule. If you put 4 fingers in the direction of rotation, then your thumb shows the direction of the torque. So what do you think the direction of torque is? Is it torque of magnetic field should be in the positive z direction or negative z direction? Yes, positive z direction. So if you put your 4 fingers in the direction of the rotation this way, as I said, you see that your thumb shows toward yourself or out of the page, which is in positive z direction. And the torque of gravity is in the negative z direction, so they can cancel each other. All right. So what magnetic field, which direction of magnetic field creates the torque in that direction? Again, you need to use torque equal to mu cross B to see which direction should be B, so that the torque is in the positive z direction. And this is mu. And again, if you want the torque to be in the z direction, you put your thumb in the direction of z and then see which direction should mu turn into, so that your thumb shows in the z direction, which then you come up with the B field being in the positive y direction. All right, so so far we find the direction of the magnetic field parallel to the y-axis that will cause the loop to swing up until this angle. And now we want to find the magnitude of the field. All right. How do I find the magnitude of the field? Any ideas? As I mentioned, at this angle of 30 degrees, the torque of the gravity and torque of magnetic field, they cancel each other. So the loop will be in equilibrium. So what is the torque of each one of these? What is torque of gravity? So torque due to gravity should have the same magnitude as torque due to magnetic field. Torque of gravity is, you see, the force times distance. This is the distance, half of this length, which is 8 centimeter, and times the weight. So torque of gravity will be 4 centimeter, the length, times mg, times the angle between the force and radial direction, which is the 30 degrees, sine of 30 degrees. Torque of magnetic field will be mu times B times sine of the angle between mu and B. You see this angle. What is that angle? Sine of, that's 60 degrees. All right. So we have G, we can find the mass using this 15 gram per centimeter. What is the total length of this? the length of that is 2 times 8 centimeter plus 2 times 6 centimeter. So this is 28 centimeter, right? And then 15.15 grams per centimeter. So the mass will be 0.15 gram per centimeter times 28 centimeter. So you can calculate that. 0.15 times 28, you get 4.2 grams. Right? And 4 centimeter is, we can write everything in SI units and solve for B. And what is mu? Mu has a magnitude that is, what is mu? Anybody remembers?
Number of turns, the current and area.
That's right. The number of turns is what? NIA, yes, very good. Number of turns is 1, right? The area is the length times the width. So 0.6 times 0.06 times 0.08 meters, right? This is the area times the current times 8.2. Right? How much that comes to? 0.06 times 0.08 times 8.2 becomes 0.03936. 0.03936 amp meter square. Okay, this is mu. Then B becomes 0.04 centimeter times M, which is 0.0042 in kilograms, and 9.8 sine 30, which is 0.5, divided by mu 0.03936 times sine 60. All right. We can approximately cancel this with that. And yeah, you get about 1 point something millitesla. All right, you can calculate that. Any questions? So you see, step by step, you need to think about it in terms of what we had in the chapter. All right. Since there's no question, I'm going to move on. Here says figure shows a rectangular 20-turn coil of wire of dimensions 10 centimeter by 5 centimeter. It carries a current of 0.1 amp and is hinged along one long side. It is mounted in the XY plane at angle theta 30 degrees to the direction of a uniform magnetic field of magnitude 0.5 Tesla. The unit vector notation, in unit vector notation, what is the torque acting on the coil about the hinge? All right, so what is the, we want to find the torque in unit vector notation. So torque is mu cross B. So we have B here. We can write it in unit vector notation. What is mu?
NIA.
NIA, but that's correct. Mu has a magnitude NIA. What direction?
Well, is it negative Z?
That's correct. Very good. You put your 4 fingers in the direction of the loop, current in the loop. You see your thumb shows perpendicular to that is negative Z direction. So this is a negative k hat. So now you have mu, and what about b? If I want to write b in unit vector notation, what should I do? B, you see, it has two components, x and z. It doesn't have y component. So we can say magnitude times cosine theta, right? So 0.5 Tesla cosine 30 degrees in I hat direction, and 0.5 Tesla sine 30 degrees. Oops. Sine 30 degrees in k hat direction, right? So you can write all of that. What is 0.8 cosine of 30 is 0.866 divided by 2 becomes 0.433. So becomes 0.433 I hat plus 0.25 k hat. This is B in unit vector notation in SI units, right? And what about mu? Mu is as NIA. N is 20. I is 0.1. And the dimensions are 10 centimeter by 5 centimeters. So 0.1 times 0.05, right? So that gives you 2, and this gives you 0.1. So sorry, this gives you 2, and in the negative k hat direction. So it becomes 2 times 0.05 becomes 0.1 times 0.1, 0.01. And there's something wrong with my pen. 0.01 in negative. Let me write more neatly. Negative 0.01 k hat. All in SI unit, amps meter square. And this is in Tesla. All right, now we can say tau is equal to mu cross B. Tau is equal to mu, which is negative 0.01 k hat cross B, which is 0.433 I hat plus 0.25 k hat, right? I don't need parentheses. All right, now if I want to do this, you see k hat cross k hat is 0. I don't need to do that. And the other one, k hat cross I hat, is what? K cross I is j, right? We have a negative sign, so it becomes negative j hat, and the value is 0.00433 and j hat, right? So we multiply the magnitudes and then multiply k cross I hat. K hat cross I hat is j hat, and we have a negative in front of it. That will be Newton meter. Or we can write negative 4.33 j hat millinewton meter. All right. Or 4.33 times 10 to negative 3 Newton meters. All right. Any questions? Okay. Moving on. An electron at point A in figure has a speed V naught of 1.41 times 10 to the 6 meters per second. Find the magnitude and direction of the magnetic field that will cause the electron to follow the semicircular path from A to B. And B, the time required for the electron to move from A to B. All right. Any thoughts? First, which direction should the magnetic field be? if it is to be going around this circle or semicircular path. What do you think? Direction?
Yeah, to the right.
Like this?
That's what I'd assume.
All right, if the magnetic field is this way and the velocity is that way, we said that the magnetic force is what? F is Q V cross B, right? You can think, it is okay to just throw in ideas, and then you should be able to verify if it is right or wrong. So if you do V cross B, you see, you turn your fingers from V to B, if this is B now. Which direction is the force?
Into the page, right?
Into the page is V cross B, that's correct. But because electron negative
Oh yeah, so out of
becomes
the
out of
page.
the page. So you see, if the force is out of the page, it wouldn't go this way, would it?
It wouldn't.
Yeah, so that means that probably this is not the right answer.
So it's the other way.
So somebody again said, sorry? So we are trying to find the direction of B field that causes electron to go on this circle. Remember, we said that when it is a cross product, when it is a cross product, the cross product is perpendicular to both V and B. So F is perpendicular to V, and B isn't. B is also perpendicular to both F and V. So what is the direction of force at this moment that is shown in the figure? What is the direction of the force? See, it's going on a circle. The force is centripetal, right? So the force is in fact this way, not B. Oh. The force is in this direction. If the force is to be in this direction, what direction should the B field be? So if, yes, B is into the page, if B is into the page means this, we show by crosses. So what is direction of V cross B? V cross B will be to the left, right? But because it is an electron, the force will be opposite, which is in that direction. So B is into the page, right? Because V cross B is to the left, and then because electron is negative now, you flip it, becomes to the right. So the direction of B field is into the page. And what is the magnitude of B field? We said that it's going on a circle of radius r, right? We said that r is equal to mv divided by q times b, absolute value of q, right? And therefore b will be mv divided by qr. If you solve for b, you can find the B field like this. So B will be, magnitude of B is mass of electron, 9.11 times 10 to the negative 31st kilogram, times V, which is given 1.41 times 10 to the 6 meters per second, divided by charge of electron, which is 1.6 times 10 to the negative 19 coulomb, times r, which is 5 centimeter, so 0.05 meter. All right. All right, so the result will be amps. Sorry, the result will be Tesla because everything is in SI units. And the value is, we need a calculator. All right, you can calculate that. And then how much time requires? Do we need B to calculate the time? Because we have a speed, and we can have the length of this trajectory. So you can say T, the time, is equal to pi R, or pi capital R, we called it, over V, right? V is equal to distance divided by time. Time is distance divided by V. So it becomes 3.1416 times 0.05 divided by 1.41 times 10 to the negative plus 6 meters per second. So this is meters divided by meters per second becomes seconds. Okay, you can calculate that as well. All right, any questions? All right, let's move on. In this example, it says, in an experiment with cosmic rays, the vertical beam of particles that have charge of magnitude 3e and mass of 12 times the proton mass enters a uniform horizontal magnetic field of 0.25 Tesla and is bent in a semicircular direction, semicircular diameter, 95.0 centimeter, as shown in the figure. Find the speed of the particles and sign of their charge. Is it reasonable to ignore the gravity force on the particles? How does the speed of particles as they enter the field compare to their speed as they exit the field? So there are three questions. Let's find the speed of the particles and sign of their charge. But in fact, speed and their sign. 4 questions. So what is the sign of their charge? Can anybody tell? Are they positively charged or negatively charged? No ideas? From their motion, you see the B field is out of the page, isn't it? And the velocity is, Ryan, you said negative. Why is it negative? Can you talk? All right.
Wait, is the arrows the curve, is that speed?
Yeah, the particle is moving this trajectory like that in this direction. Yeah, that's the direction of velocity is showing, yes. So they're going this way. This is V, right? And then what is V cross B? The force, remember? The force is Q V cross B. V cross B is in which direction? B is out of the page. Is V cross B to the left or to the right? Turn your fingers from V to B. Your thumb shows which way?
Left.
Left, yes. This is V cross B. This is V cross B, but the force is this way, centripetal, right?
Yes, this is curving, yeah.
Yes. All right. So you see that VF and V cross B are in opposite direction, means that Q is negative, right? F and V cross B are in opposite direction. Therefore, so the Q is negative. Right? Very simple math, right? And then what is the speed? Again, we can write, we have that formula for radius, so we can use it. R is equal to mv over qb. And we know the magnetic field and we know the radius. So V is the speed. V is equal to QBR over M. So V is equal to 1.6 times 10 to the, 3 times 1.6. 3 times 1.6 times 10 to the negative 19. This is charge because it says 3 electronic charge times B, which is 0.25, times R, which is, this is diameter 0.95. The radius will be half of that, 0.475, divided by the mass. 12 times proton, 12 times 1.67 times 10 to the negative 27. Okay, this is how fast they're going. You can calculate that. B, is it reasonable to ignore the gravity force on the particle? What do you think? So you see, these are ordinary numbers, 3 times 1.6, you give and 12, but you have 10 to the 19 over 10 to the negative 27th. That's 10 to the 8th. And the speed of the particles is in the order of 10 to the 7th. And the radius is less than a meter. So the acceleration of the particle, acceleration, not the magnitude of the acceleration, is V squared over R. And V is in the order of 10 to the 7th, right? Or maybe 10 to the 6th at least. So there will be 10 to the 12th, 10 to the 6th squared over 0.5, I'm estimating. So that's 10 to the 13 or 12. The acceleration is in the order of 10 to 12. But what about the gravity? Acceleration of gravity is 10. So this is so much bigger than the acceleration due to gravity. So we can ignore the acceleration due to gravity, therefore ignore the gravity force on the particle. This is meters per second squared. This is meters per second squared. Okay? Any questions?
Professor, can you explain real quick why it's pointing to the left for the V cross B?
Yeah, you put anytime you want to calculate the cross product of two vectors, you put your 4 fingers of your right hand in the direction of the first vector, which is downward, and then turn into the second vector, which is out of the page. And your thumb shows the direction of the cross product. Does it make sense?
B is out of the page?
Yes. You see when it's shown by dots. Remember we said when it is.
Oh yeah, and when it's crossed, it's okay.
Yeah, into the page. Yeah, cross into the page, dot is out of the page. All right. Everything clear? All right. So now we want to see how does the speed of the particle as they enter the field compare to their speed as they exit the field. Means that what is this? If the speed here is v, what is the speed when it goes this way? V prime. What do you think? This requires some knowledge of mechanics. Remember, the velocity vector is always perpendicular to the force. You see, because this is the velocity vector, this is the force. By definition, cross product is perpendicular to both of the vectors, right? So if F is perpendicular to V, therefore the acceleration is perpendicular to V always. And therefore it only changes the magnitude of velocity. It doesn't change the, sorry, I said the opposite. It only changes the direction of velocity. The acceleration only changes the direction of velocity. It doesn't change the magnitude of velocity. So how to compare the exit v prime compared with v? They are the same. You can look at it in a different way. You know, remember work energy theorem. It says the work done on a particle is equal to change of its kinetic energy. But when force is perpendicular to the direction of motion, work is zero. Therefore, change of kinetic energy is zero. All right. Right. There are different ways of looking at it. So v prime is equal to v. This is exit speed. Is entrance exit entrance speed. All right. They are the same because magnetic force doesn't do work on the particle because it is perpendicular to the direction of motion. All right. Questions? All right, let's go to the next. A long wire carrying 4.5 amp of current makes two 90-degree bends as shown in the figure. The bent part of the wire passes through a uniform 0.240 Tesla magnetic field directed as shown in the figure and confined to the limited region of space. Find the magnitude and direction of the force that magnetic field exerts on the wire. So you see that this part from here to here of the wire is in the field. And the field is out of the page. As you see, it is denoted by dots. And now each part of this, you can break it into three parts. One part, two part, and three parts. So you can call them 1, 2, 3 if you want. And so let's make part 1, part 2, part 3. And of course, the length of part 1 and 3 is not given, but doesn't matter because the direction of the forces are in the same. What is the direction of the force on part 1 and 3? Is it left, right, up, down, into the page, out of the page? The B field is out of the page.
Is it down?
Yes, how did you do that?
Right hand rule?
Yes, right hand rule. Put F is equal to I, remember I L cross B. So L is in the direction of the current. So you put your 4 fingers in the direction of current in the, which is this way, and then turn it into B, which is out. So then the force will be down. The force F1 and F3 will be down. What about the force on part 2?
To the right.
Yes, to the right. So again, you put your 4 fingers in the direction of, so this is F2. You put 4 fingers in the direction of the current, which is up the page, and then turn into out of the page. Your thumb shows the direction right. So these are the directions. And what are the magnitudes? F1 plus F3, you can do that together. This here becomes I, L1 cross L1 times, if they are perpendicular, we can just write the magnitudes. Just write the magnitudes. L1 I, L1 B, I LB, and plus I L2 B. So you see it becomes I L1 plus L2 B, which is 60 centimeter, right? So F1 plus F3 magnitude is equal to I. What is I? 4.5 amps. L1 plus M2 is 60 centimeter, which is 0.6 meters, times a B, which is 0.24. So you can calculate that. This is the direction. This is F1 and F3 that are both downward. And F2 is I L2 times B. L2 is 30 centimeters, so will be half of that. 4.5 times 0.3 times 0.24. So how much is that? 4.5 times 0.3 times 0.24. So it becomes 0.3888. 0.3888. What is the unit? Times 2. That becomes 0.7776. Units are? What's unit of the force?
Newton.
Newton. Yes. All right. So you have these, and so you have a force in this direction, force in that direction. You can say the force will be in some direction like this. You see, this is F1, F2, and this is F13. So F net will be sum of these two, which is like vector sum of these two, right? What is the magnitude? Because they are perpendicular, becomes this squared plus the other one squared, 0.3888 squared, in square root. So you get 0.87. So F net of F net is 0.887 Newton, and the direction will be, tan inverse of 2, right? It's this divided by that will be tan of theta. So theta will be tan inverse of 2/1. How much is tan inverse of 2/1? Becomes 63 degrees. So this theta is 63 degrees. So magnitude and direction. Find the magnitude and direction of the force that the magnetic field exerts on the wire. If you look, you see that this is exactly a force that would be applied to a wire like this, right? If the wire was connecting this point to this point directly, it would have the same force acting on it. So it means that in general, it doesn't matter if it is a uniform field, it doesn't matter how the wire is in the shape of the wire inside the magnetic field. It just depends on where it starts, where it ends, which is very interesting. All right. Any questions? Okay. This one. A thin 50 centimeter long metal bar with mass of 750 grams rests on, but is not attached to, two metallic supports in a uniform 0.45 Tesla magnetic field as shown in the figure. A battery and a 25 ohm resistor in series are connected to the support. What is the highest voltage the battery can have without breaking the circuit at the support? The battery voltage has the maximum value calculated in part A if the resistor suddenly gets partially short circuited, decreasing the resistance to 2 ohm, find the initial acceleration of the bar. All right, so here we have the voltage and resistor connected to this. So obviously it sends the current through, which is in this direction. And doesn't have, it has negligible compared to this 25 ohms. It has negligible resistance. All right. We want to see what is the V max so that this leaves the support. How would this leave the support? It has 750 grams, so the gravity is pushing it down. The magnetic force, which is I cross B, you see this is I, B is into the page. So if you use right-hand rule, you see that there's a magnetic force, FB, pushing it up. This is F of gravity, that's F of B. So at the critical voltage that these two forces are the same, we say ILB is equal to mg. That's force of the magnetic field is opposite of, let me write only magnitude, not the vector. Force of B is equal to force of gravity. And I is V over R. So V over R, the resistance, LB is equal to mg. So V will be mg R over LB. So we can, M is 0.75 times, let's say 10 times 25 divided by L was 50 centimeter times B was 0.45. All right, so you can find that this and that becomes 1.5, this becomes 15. 15 times 15 and 0.45 becomes 1/3. That's not a round number. So 15 times 25 divided by 0.45 becomes 833. So V max will be 833 volts. Now it says, B, the battery voltage has the maximum value calculated in part A if the resistor suddenly gets partially short-circuited, decreasing its resistance to 2 ohm. Find the initial acceleration of the bar. What do you think? So if suddenly the V is the same, but R becomes 5 times smaller. Sorry, it becomes 25 to 2 ohm, becomes 12.5 times smaller. So you see the magnetic force becomes, the current goes 12 times bigger. The magnetic force becomes 12 times bigger. So now FB is equal to 12 force of gravity, and F net, therefore, 12.5, sorry. F net becomes force of magnetic field minus force of gravity, which is 12.5 force of gravity, mg, let's say, minus mg, which is 11.5 mg. So what is the acceleration? Acceleration is F net over m, which is now 11.5 g. So if you want to use 10, so it will be 115 meters per second squared. So it jumps up very fast. All right. All right, that's all the time we have. Have a good night, and I see you on Wednesday.
You have a good one, Professor.
You too.
Have a nice day, Professor.
You too. Thank you.